Hey guys, how you doing? And it's Lajora here again, back with another video from BHM at GCSE Chem. And today we're going to be doing section C3.7, which is giant covalent structures. And basically, I haven't been able to put the links to my videos of C3.2, C3.3, C3.4, C3.5, and C3.6. And I'll be doing C3.7 today, which is all about giant covalent structures. And then hopefully I can upload it. I'll put the links to my website that you can, then you can check my website out, fully updated by today. If not, by the end of this week. I do apologize, I'm not very up to date with putting the links to my website, but yeah, hey ho. And yeah, so again, I'm back. I'm in my room today making the video. Don't want to disturb the family downstairs, so that's why I just came in. Came here in my room. Came here to film the video in my room. And yeah, so the book I'm using, by the way, is this one. It's the AQA GCSE Chemistry Revision Guide from Caboodle. Yeah, that's the book I'm using. And then, so yeah, and what else do I have to mention? So yeah, after this section, we'll be more than halfway done with this chapter. So that'll be good. And yeah, so let's begin without further ado. And if you're following the student book, it's pages 48 to 49 that you want to be looking at for this lesson. So that's the big textbook, obviously, the red one. And yeah, so today's obviously C3.7, section C3.7, which is called giant covalent structures. So some substances, such as diamond, form huge networks of atoms held together by strong covalent bonds in giant covalent structures. And what does that mean? So basically, substances like diamond, they form huge network of atoms, or huge networks of atoms, by the way, make it plural, that are held together by strong covalent bonds, and they, in giant covalent structures. So diamond has diamond has giant covalent structure, basically. That's what this is getting at. And each atom in the structure is joined to other atoms by strong covalent bonds. Basically, diamond, each atom in this, each atom is in the structure is joined to other atoms by strong covalent bonds. So that's the thing. There are very strong covalent bonds between the atoms. And it takes an enormous amount of energy to break down the structure, and so these substances have very high melting points. Now that's the reason why diamond, diamond or any, these giant covalent structures, why these substances basically have very high melting points. Yeah, I don't think they gave an example in diamond in the first paragraph, but it could be any giant covalent structure basically. And these, each atom is joined to other atoms by strong covalent bonds. Lots of energy is required to break down these structures, and therefore these substances have very high melting points. So yeah, diamond is a form of carbon. So now we're going on to the next point. Diamond is a form of carbon with, or you could even say allotrope of carbon. I think allotrope is better. They both mean the same, but terminology-wise, I would use allotrope. But in this book, it says diamond is a form of carbon, but allotrope just means, allotrope of carbon means form of carbon. But if you want to use form of carbon, I don't think you're gonna get penalized for it. But I like using technical language. I believe it's more impressive to the examiner. But if they're the same meaning, it really doesn't matter. But yeah, so basically diamond is a form of carbon, or you can say allotrope of carbon, with a giant covalent structure. Now each carbon atom forms strong covalent bonds with 4 other carbon atoms. Now that's the important thing. We know that carbon atoms form 4 covalent bonds. We know carbon forms 4 bonds. We know that. Or if you didn't, you probably know. If you didn't know that, you know it now. But we know that carbon forms 4 bonds, and in diamond, that's exactly what happens. So in diamond, what happens is basically diamond is a form of carbon with a giant covalent structure. So we know diamond is a giant covalent structure, and each carbon atom forms strong covalent bonds with 4 other carbon atoms. This makes diamond very hard, and obviously, and with a very high melting point as well. So that's why diamond has a very high melting point as well. So that's important. That's important to know that diamond is, diamond has a giant covalent structure, So diamond is an allotrope or form of carbon with a giant covalent structure. You need to know that, and you need to know that each carbon atom in diamond forms strong covalent bonds with 4 other carbon atoms in, that's what happens in diamond basically, and this is what makes diamond very hard, and it also has a very high, with a very high melting point. Yeah, that's very important. So here's a question, the first question of 2 in this section, basically, why does diamond have a very high melting point? Well, we know that diamond has a giant covalent structure, and where each carbon atom basically forms strong covalent bonds with 4 other carbon atoms, and basically lots of energy is required to overcome, or you can say break the structure, break these strong covalent bonds basically, and break these bonds between the atoms, break these strong covalent bonds between the atoms, and therefore diamond has a very high melting point. So because lots of energy is obviously required to break these strong covalent bonds. So hopefully that makes sense. Let me just check just to make sure that I am right. And each atom is joined to 4 other carbon atoms, 4 other atoms by covalent bonds. Yeah, I said that. And so large amount of energy is needed to break the many strong bonds. And I'd specify strong covalent bonds, because diamond has a giant covalent structure where each carbon atom is bonded to 4 other, is covalently bonded to 4 other carbon atoms basically. I'd mentioned the word, covalently bonded and covalent bonds. I'd mentioned that, and I'd even mentioned that it's the carbon atoms. Each carbon atom is bonded to 4 other carbon atoms. So basically, what I mentioned before looking at the answers, I think that's a better answer what I gave. But yeah, you know the answer from the book as well now. So now we know that diamond. Okay, now we need to know that diamond does not conduct electricity, right? Now, as well as diamond, graphite and silicon dioxide, also known as silica, have giant covalent structures. Now that's very important. So the 3 main structures you need to know in this section are basically diamond. 3 main giant covalent structures you need to know for this section are diamond, graphite, and silicon dioxide, which is also known as silica. And silica is basically the way you spell silica is basically SILICA. So yeah. These 3 have basically giant covalent structures. So it's diamond, graphite, and silicon dioxide, also known as silica. Now in graphite, each carbon atom forms. Now we're looking at graphite. So we looked at diamond. Now we're looking at graphite. Now in graphite, each carbon atom forms 3 strong covalent bonds with 3 with other carbon atoms. Basically, that's important. Now in diamond, what we have is each carbon atom forms covalent bonds basically with strong covalent bonds with 4 other carbon atoms. Basically, each carbon atom is bonded to 4 other carbon atoms covalently in diamond. But here in graphite, each carbon atom forms 3 strong covalent bonds with other carbon atoms. So in graphite, basically, each carbon atom is bonded to 3 other carbon atoms covalently. And but in diamond, obviously, we have that each carbon atom is bonded to 4 other carbon atoms covalently. So hopefully that makes sense. And basically, they form hexagonal rings. So in graphite, you have hexagonal rings, and these are arranged in giant layers. Now, these layers, there are no covalent bonds between the layers in graphite, obviously, and because there are no covalent bonds, it means that between the layers, you only have weak intermolecular forces, which can slide over each other. These layers can slide over each other quite easily, and this makes graphite soft and slippery. So I know there's probably a lot of information, but I can't really help you much in this. It's just that it's quite logical, really. Is that in graphite, basically each carbon atom is covalently bonded to 3 other carbon atoms, and basically you have you have hexagonal rings that are formed with a giant, which are arranged in giant layers, and basically there are no covalent bonds between these layers, so there are only weak intermolecular forces between the layers, and these layers can basically slide over each other quite easily, and this makes graphite soft and slippery. You just need to remember that. There's not much. There is quite, it's just remember a story, and that should help you remembering. This happens, and this is, then this is that, this is that, this is that, and hopefully this will help you I'm going to talk about a bit of the properties of graphite and explain its structure as well. So so we've gone through that, and then in graphite, one electron from each carbon atom is delocalized, rather like electrons in a metal. Now these delocalized electrons allow graphite to conduct heat and electricity. Now let me explain that. Basically, we know that each carbon atom is bonded to 4 other carbon atoms. We know that carbon can form 4 bonds, right? And in diamond, basically, that's what happens. You know, each carbon atom is covalently bonded to 4 other carbon atoms. But in graphite, you have each carbon atom is bonded to 3 other carbon atoms, which means there's 1 electron left, because there's 1 bond left, basically. So there's 1 electron in each carbon atom that is delocalized. Now, delocalized means free to move, and it's rather like in a metal, rather like electrons in a metal. Electrons in a metal are delocalized as well. They move as well, which we're going to look at in actually section C3.9, which is about and also, you know, C3.10 as well, when we're basically bonding in metals is C3.9, and then giant metallic structures is C3.10. But for now, just remember that graphite, because 1 electron from each carbon atom is delocalized, because remember in graphite each carbon atom is bonded to 3 other carbon atoms, meaning that 1 electron is delocalized in each of the carbon atoms. And these delocalized electrons allow graphite to conduct electricity, heat and electricity. So these delocalized electrons are what allow graphite to conduct heat and electricity. So hopefully that makes sense, because remember each, graphite each carbon atom is bonded to 3 other carbon atoms, but carbon forms 4 bonds. So there's obviously 1 bond remaining. So 1 electron in each carbon atom is delocalized. And therefore, delocalized, that means they're free to move. Delocalized electrons are basically electrons which are free to move, and these delocalized electrons are what allow graphite to conduct heat and electricity. These delocalized electrons are what allow graphite to conduct heat and electricity. Now that's now it's very important to actually mention that each carbon atom contains delocalized electrons. There's 1 electron delocalized in each carbon atom. And it's not that 1 electron, there's 1 electron that is delocalized in the whole of the graphite structure. No, there's 1 delocalized electron in each carbon atom of graphite. Because, obviously, graphite is an allotrope or form of carbon. It has many carbon atoms, so there'll be many delocalized electrons, and it can conduct heat and electricity because of these delocalized electrons. So hopefully that makes sense. And these are basically the structures. Here's the structure. Hopefully you can see it properly. I don't know if you can see it, but basically here's the structure of diamond there, and here's the structure of graphite. And I would recommend you still learn these, because these are quite important. You take your time learning these structures, just in case they come up. They don't really come up. They don't really ask you to draw the structures, but just in case. And sorry about the noise there was probably some noise there, but background noise. But yeah, now question number 2, and the last question of the section, is that give 2 similarities and 2 differences between diamond and graphite. So obviously two similarities are that but they're both giant covalent structures. You can say they both have very strong covalent bonds. What else can you say? Differences, you can say that diamond can't conduct electricity, but graphite can conduct electricity. And you could also say for another difference is that diamond is hard, whereas graphite is soft and slippery. Similarities, you can say actually that they are both giant covalent structures. That's one. And then also they both have very high melting and boiling points. So that should be 2. And there are probably many others, which I'm going to go through. I'm going to go through all of them. They're all the answers in the book, but in the mark scheme. But I've just said 2 similarities and 2 differences. So yeah, let's just see. So yeah, there's quite a big list. So similarities are that there are forms of carbon. You could have said, I probably could have said that as well. I just didn't come in my head at that time. But they're forms of carbon. You can say for the similarities, they're giant covalent structures, which I said, all covalent bonding. That counts as 1. So basically, you could have, So I'm pretty sure for similarities, you could have also said they have high melting and boiling points. I don't know why it doesn't say I'm pretty sure you could have said they have high melting points. I don't know why it doesn't say in the mark scheme about the similarities, high melting points, but you surely can have that as well because they're giant covalent structures. But here the similarities given off their forms of carbon and their giant covalent structures. So I mentioned giant covalent structures, just didn't mention the forms of carbon. But I'd mention high melting points, which should be right as well. They're giant covalent structures, so obviously they'd have high melting points. Now, there are quite a few differences. Let's see that. Now, differences here, it says carbon atoms in diamond are bonded to 4 other carbon atoms, only 4 carbon atoms, only 3 other atoms in graphite. Yeah, we could have said that. Like, I knew that as well. I just didn't say it, but we could have said that. Now, I did mention that diamond is 3-dimensional, graphite is 2-dimensional. That wasn't in the book, but just remember that as well. Diamond is 3D, graphite is 2D. You could also say, diamond is hard, graphite is slippery or soft. Yeah, I said that, I mentioned that. Diamond is transparent, graphite is grey or opaque. You could have said some of these aren't actually in the book. Just remember what I'm saying. Diamond is transparent, graphite is grey or opaque, you could say as well. Graphite is a good conductor of heat and electricity, but diamond is a poor conductor. Yep, I mentioned that. And graphite has delocalized electrons, diamond does not. And graphite has intermolecular forces, or you could say weak intermolecular forces to be more specific, whereas diamond does not. So there's a lot of differences there that you can just take, just remember, just note down. So yeah, hopefully that was helpful there, looking at the answers and the similarities we've been through as well. Giant covalent structures, they're both allotropes of carbon, they're forms of carbon. Allotropes of carbon and forms of carbon mean the same thing. And what is it? They both have high melting points. You can say that as well because they're giant covalent structures. And the reasoning for high melting points. We've been through that earlier in the video. And it's probably going to come up in the key points as well, maybe. Yeah, probably. But the key words for this section are giant covalent structures and delocalized electrons. Now, the key points, so they were the key words. Now, the key points for this section are, just to finish off, so they are that some covalently bonded substances have giant structures. Now, these substances have very high melting points and boiling points. So you could say have very high melting points and boiling points. Yep. So boiling points as well. The carbon atoms in diamond have a rigid giant covalent structure, making it a very hard substance. Yep, we've been through that. There's a very rigid giant covalent structure, and diamond's very hard. We've been through that as well. And then the 2 more points remaining. Graphite contains giant layers of covalently bonded carbon atoms. However, there are no covalent bonds between these layers. So it does have covalently bonded carbon atoms, basically giant layers of covalently bonded carbon atoms, this graphite, but it doesn't have any covalent bonds between these layers. This means that they can slide over each other, making graphite very soft and slippery, because between the layers, remember, you only have weak intermolecular forces, which don't require much energy to break, basically. And then the final point is that graphite can conduct electricity and thermal energy because of the delocalized electrons that can move along its layers. So basically it has delocalized electrons that can move along its layers, and that's what allows graphite to conduct electricity and also thermal energy, or heat energy, you could say. So that's the end of this section. Guys, I thought the video ended for some reason. I thought there was some problem, but basically that's the end of the video, guys. That's the end of this section as well. C3.7 Giant covalent structures. Tomorrow we're more than halfway through the chapter, which is great. Through the 3rd chapter, which is great. Obviously, tomorrow we're doing C3.8, which is all about fullerenes and graphene. So that's also very interesting. Hopefully you found this really, really useful. This video really, really useful. Hopefully you found it, very helpful. Make sure to share, like, and subscribe. Turn the notifications on. Turn the notification bell on if you haven't already, so that you can, you're notified and updated when I upload new videos that you can watch. And what else was I meant to say? I'll try and obviously upload I'll upload this video obviously, but then I'll put the links to C3.2, C3.3 all the way up to C3.7. Hopefully by today, if not by the end of this week, everything should be updated. And thank you very much, guys. See you in the next video.